Okay, so today we'll discuss our last topic of this course, and that is power amplifiers. Usually, in the output stage, the amplifier needs to provide high power to the load. Now, the conventional amplifier that we know, right, so far that we have learned, they have certain limitations when it comes to high power, right? When the amplifier has to deliver, you know, large current and large power to the load. So let's see first what are the limitations, right, for the our regular amplifier, right, in delivering high power to the load. So this is just our a conceptual diagram of a regular amplifier. So here the two types of current flows in the regular amplifier. One is our DC bias current, which is IC, and the other is the our signal current, which is denoted by small letters, right? Small I, small c. And this is the collector terminal where we'll have the DC collector voltage, VC, as well as we'll have our small signal collector voltage represented by small v and c. And this is our base to emitter terminal where we have the forward bias base to emitter voltage, DC base to emitter voltage. In addition, we'll have the small signal base to emitter voltage. So this is how we can represent the different the current and voltage components of this circuit. Now, what is the power output of this circuit? So power output, okay, let's say these are P out, denoted by P out. The output voltage times the our input, sorry, the output current, right? So that is instantaneous. So if it is an AC, so what we do for AC signal, we take the RMS values, right? RMS values of the voltage and the current. So that is our output power. So this actually V naught I know the small signal voltage and current. These are nothing but our this the collector voltage and the collector current. So this also we can represent in terms of small signal collector voltage VC. Right? So that is our RMS value of VC, and the small signal collector current IC, the RMS value of the collector current. So that will be our output power. And then input power, let's define as P in, and let's our input power P in. What is the input power? Can anybody say what will be the input power in this case? Hello guys, what will be the input power? Hello, what is the input power of the amplifier?
Sir, it would be like Vi multiplied by small I input current.
No, here is the small signal voltage, no? That is the input power is the represented by the power supplied by the DC supply, right? So the bulk of the power comes from the DC supply, right? So that is VCC times the IC, right? So that is the input power. That is what the amplifier is getting its power from the DC supply. That's why we have DC supply, right? And amplifier then amplifies the small signal voltage, right? And gives high power at the output. That DC power is converted into AC power, right? So these are the power input, right? That comes from the power supply, and that's the biasing, right? Biasing means also powering up the amplifier, right? So now let's calculate this the output power in terms of the input power. How much we can have? We have shown you these diagrams before. The diagrams of the the voltage and current for the amplifier. Let's say this is our time axis, right? And here we want to show the voltage, right? Now let's say this is our voltage here is our maximum voltage that we have for the supply VCC, right? So this is our supply voltage. And somewhere in the middle, let's say we have the collector voltage VC somewhere here. Somewhere here we have the VC, right? Now at the collector, you have the small VC that is superimposed, right, on this DC collector voltage. And when you add these two, so VC will, the signal collector voltage will write on the DC bias voltage. It will look like this. So this part is our small signal collector voltage. So similarly for collector current, we can also have this drawing. So let's say this is our time axis again, and this is our current. How do I represent? Let's say this is just our current I. And then uh, let's say this is our current DC collector current IC. Now superimposed on this collector current will be our small signal current IC, and that will look like this when you superimpose the current, signal current on the bias current. It will be something like this, right? So that is our small signal current IC. So now this part here, this is our the maximum value of VC here, V not max. And this is our maximum value of IC. Now from the diagram, as you can see, let's say this part, right? If this is VC is at the middle, so we can say that this is VCC by 2. Let's say if you put VCC halfway, right, of this VC halfway of this VCC, then you can have maximum swing of the collector, the small signal voltage, right, for both the cycle, positive and negative cycle. In that case, if you we can say that V naught max, the maximum value of the output voltage that we can have should be less than or equal to VCC by 2, right? This maximum value should be less than this half of VCC, otherwise your voltage will get truncated and you will get distortion, right? For the collector current, same goes for the collector current. Here you see that IC max, the maximum value of the current, should be less than the bias current IC, otherwise your current will get truncated. So in this case,
Sir,
yes,
sir, can we like represent this VCC by 2 in terms of your VCC minus VC?
yeah, that's also okay, but the VC is half set at a half of VCC by half of VCC, right?
Oh, okay, sir.
So that's why, yeah. So, and in this case, IC max should be less than or equal to our collector current IC. So the maximum value for V naught max is half of VCC, and maximum value of the IC naught is IC max is IC. Now coming back to our this expression for P out, right? P out, which is we have expressed as V naught, the RMS value, and the collector current, alternate collector voltage, RMS value, right? And RMS value, how do we get RMS value? What is the RMS value, guys?
Sir, peak value by root 2.
Right, peak value, right? So the let's write like this: the peak value of the collector voltage divided by square root 2, right? So that will be RMS value. Similarly, for collector current, the peak value for the collector and ICP divided by square root 2. Right? So that means it is half of peak value of collector voltage and peak value of collector current. Okay. Now P out, what is the maximum output power we can have for this amplifier?
Sir,
Yes.
sir, I'm having a little confusion with the IC max expression. Like, wasn't it supposed to be greater than equal IC?
IC max
Yes, sir.
greater than IC. How? If you have a large value, so what happens? This part,
Yes, sir. This one falls below zero, sir.
current becomes negative. Negative
Negative.
means
Yes, sir.
it will go upward, right? But
Sir,
current
it
cannot
means
flow
the
upward.
transistor will go into cutoff region, right?
Okay, let me take a pause because of the other starting. Okay, guys, what is the question?
Sir, I got the answer, sir.
Hmm?
Sir, I got the answer.
Okay. So, what will be our maximum output power? Maximum output power will have when this V naught max is will have its maximum value, and IC max will have its maximum value, right? The peak value, right? They will have their maximum values, and maximum value is for the voltage is VCC, half of VCC, and for current is IC. So these are the maximum values we can have for this voltage and currents, right? So if you put these maximum values here, so the maximum power will turn out to be VCP is our half of VCC and current is IC, right? So that gives us 1/4 of VCC and IC. So that is the maximum output power we can have, right, with this amplifier. Is that clear, guys?
Yes, sir.
So that is the theoretical maximum value, and the maximum value, of course, is let's say determined by the supply voltage and the bias current. So if you want to have higher output voltage, higher power, so then you need to either increase the supply voltage or the bias current, right? So now, what is the efficiency of this circuit? Efficiency, the maximum efficiency for maximum output power. So that will be determined by output, the maximum value for the output given by P in, right? So you see that P in, so this part, right, basically our input power, right, P in. So that's already we have shown here, right, is our P in. So maximum output power is, efficiency is 1/4, or that in terms of percent is 25%. So that is, I mean, theoretical, right? But for practical amplifier, efficiency is even less than that because of other losses in the circuit that hasn't been considered here. And of course, the VC, IC, these are the maximum. We have considered half of VC. These are the maximum values, but usually for practical amplifier, these are taken. I mean, we cannot go exactly this maximum, reach exact this maximum values. We have to stay little bit lower than these values. So for considering all these factors, actually the maximum efficiency for these amplifiers are usually less than 20%. Right? So that is what you can achieve with our regular amplifiers, the maximum efficiency only, only about 20%. So you see that 80% of the power, right, that is used or supplied to the amplifier is actually wasted, right? That is not delivered to the load, and it is dissipated as heat in the circuit. Is that clear, guys? Any
Yes, sir.
question? So what are the issues here when the at the output you need to deliver high power to the load, right? Then your battery needs to supply high power, right? Battery has to supply that power. Now, but 80% of the total power supplied by the battery will be wasted, right? So it will quickly drain out the your battery, right? And the since 80% of the power is dissipated as the heat in the circuit, so it will cause uh, maybe I mean a tremendous amount of rise in temperature in the circuit, and it may damage your circuit and shorten its lifetime, deteriorate its performance, right, or related to the high temperature. Right? So this is really a big problem. I mean, draining out of the battery is one problem, but the bigger problem is because of huge temperature rise, it may ultimately damage your circuit. Is that clear, guys? Any question? No question?
No, sir.
Okay, so how do we solve this problem? Now, if you design an amplifier with IC0, is it possible to design an amplifier with IC no bias current? Because if you can make IC0, then P in can be zero. Right? So here in the circuit, we're assuming that IC is 0. When will be IC 0? So if the base emitter voltage, the DC bias voltage, the forward bias voltage is 0. If there is no forward bias voltage here, right? So there is no, when this junction remains off, right? If this junction remains off, the DC bias current IB will remain 0. IB will remain 0. And as long as IB remains 0, since IC is beta IB, right? IC also remains 0. Right? So how this transistor will operate then, right? So here this will function in this way that when this VBE, VI, the input voltage VI is same as VBE, right? When this VBE is greater than or equal to the base to emitter voltage. When this input voltage exceeds the forward bias base emitter voltage, this will turn on, right? This turn on and IC will flow, right? IC the signal current, and this will flow in accordance with the variation in the base to emitter voltage. So what happens here? Let's say you have this time axis, and then here uh, okay. So this is your, let's say, VI, input voltage. Input voltage something like this, going like this. And let's say this is our VBE. So this our input voltage is varying, and this is the point where it exceeds the forward bias based emitter voltage, and this is our V naught. Right? So the transistor turns on when VI is greater than VBE, right? So the transistor is on, right? Transistor is on, and we have IC will flow, right? And V naught will increase, right? So V naught will remain 0 until the VI, the input voltage reaches the forward bias base to emitter voltage. And when this happens, IC starts flowing and V naught will rise. So V naught will initially remain 0 until this point, and then it will increase, right? And then again it will decrease, and then it will become 0 when VI reaches VB, it goes below VB, transistor turns off, and output goes to 0. So, and for the rest of the cycle, since VI is negative, right? VI goes negative, the transistor remains off. And again, when VI exceeds this forward bias voltage, so VI, again V naught increases and then goes to 0. Right? So this is how we'll have the output voltage, right? So that is how output voltage will vary, right, with input voltage Vi. So we don't get a complete cycle, or we don't get even complete half cycle. We get a bit less than the half cycle. And in this case, the P in, what will be our input voltage, input power? Input power will be our VCC times the collector current IC, right? And IC will be there whenever we have the VI, whenever Vi exceeds this VB. Otherwise, IC also remains zero. So actually, in this case, we have take the average power and VCC times IC and 0 to T, right? The average power of this. So that will be your input power. And in this case, input power will be a lot less because IC most of the time remains zero. Only IC flows only when the transistor is on, right? Which is IC is same as our the signal current or the output current. So in this way, we can improve the efficiency a lot, right? If we use this technique. Any question, guys? Any question? Is it clear? Okay, now this is for regular amplifier. Now at the output stage, this is a common emitter amplifier, right? We have explained the concept and the limitations of our regular amplifier in delivering the the high power to the load. This is our common emitter amplifier, but at the output stage, we usually have common collector. So how does it work out for common collector? So this is what is known as the push-pull output stage. This is push-pull common collector output. How does it work? We have two transistors there, as you can see, and the bases are tied together. We have applied this Vi here. Now, here we have this now base to emitter voltage. There is no bus voltage here now till now. Here base to emitter voltage VBE. This is a PNP transistor. So here we need a VEB plus minus, right? So these are the forward bias voltage. These are not here until Vi exceeds this, these voltages, and they can supply this voltage. So basically, these transistors they remain off, and the output voltage will be zero, right? So for to have an output voltage, you see that if Vi is less than VBE, right? If Vi is less than this forward bias voltage, So Q1 remains off, and V0 is 0, right? And if Vi is greater than minus VBE, or yeah, VEB, because this voltage has to be negative here in order for this transistor turn on, and if it is, I mean, more positive than this negative voltage, so Q2 remains off. Q2 remains off. So also V0 will be 0. So from these two, we can easily say that for Vi less than VBE and greater than, instead of VBE, we can just write VBE. So we are taking considering the magnitude. So if Vi less than VBE or greater than minus VBE, then V0 will remain 0, right? So in order for the transistor to conduct and to have an output voltage, Vi has to be greater than or equal to VBE, or it has to be less than to minus VBE, right? So only then we have an output voltage. So in the first case, when Vi is greater than VBE, the Q1 will be on, right? And when this happens, Vi goes below, then Q2 will be on, right? So during the positive half cycle, Q1 will conduct, and negative half cycle, Q2 will conduct. So positive half cycle, when this is on, right? So then current will flow this way, right? This is how the current will flow, the IN, right? So load current flows this way. This is on, right? So that is on during this positive half cycle. During the negative half cycle, when Vi goes below VBE, so this turns on, this turns off, so current doesn't flow this way anymore, and the current will flow this way. So then IL, instead of flowing down, it flows up. This flows in the opposite direction, right? So IL flows in this. This is on during the negative half cycle, right? As we have seen our previous analysis that uh, when we set the IC to 0, the transistor conducts only for half of the cycle, right? A little less than that. So here what we have done, we have used two transistors. So one PNP, the other NPN. So NPN conducts when during the positive half cycle, and PNP conducts during the negative half cycle. So the Q1 here is like pushing the current into the load, whereas Q2, it pulls the current through the load, right? So that's why this configuration, this circuit is known as the push-pull output stage. One is pushing the current, the other is pulling the current through the output. Is it clear, guys? Any question? Hello, guys. Are you there?
Yes, sir. Clear.
Yes, sir.
Yes, sir.
It feels like it's I'm talking to nobody. Okay, so okay, now let's see in a diagram. We have explained the concept, and let's see how it looks like. Okay. So these are voltage axis. Okay, so let's say these are input voltage Vi. These are input voltage. Then somewhere here we have the forward bias voltage for the base emitter junction, and this one NPN, this one for PNP. This is our positive VBE, forward bias voltage for NPN, and this is the voltage required for PNP minus VBE. Now, as we have shown here, as long as Vi, input voltage, remains below VBE, Q1 remains off. Right? So until the input voltage reaches this voltage, VBE, the output voltage will remain zero, V0 will remain zero. And then V1 will start increasing, right? When Vi exceeds this voltage VBE. So Vi when is greater than or equal to VBE, so Q1 is on, and the V0, the output voltage, the voltage here will be the input voltage minus this voltage drop VBE. So V0 will be Vi minus VBE. So here just when Vi is VBE, it is zero, and then it will start increasing. But it will be always less than our it will be always less than our input voltage by VBE. So see this difference between Vi and V0 will be always there, and this difference will be equal to the base to emitter voltage. V0 will be always less than Vi by VBE. Right? And then this turns off here when Vi reaches VBE again, and then it remains zero, right? As long as Vi then goes below zero. And then when it reaches minus VBE, right? When it reaches minus VBE, what happens? The Q2 turns on, right? Now Q2, the PNP transistor. So when Vi is less than or equal to minus VBE, so then we have this. Now Q2 is on, right? And V0 will be, in this case, Vi plus VBE. Right? Now in this case, note that Vi is negative. right? Vi is negative, and V naught here is Vi here. So Vi plus is a voltage rise, so plus Vb. So that will be our V naught. So now this negative plus, so that will be like this. At this point, this is zero, and then it starts increasing, right? And then I change this one. So it starts increasing, reaches maximum, and then it goes to zero when Vi reaches V. So again, this gap here, so between V naught and Vi, so this will be always equal to Vb. And then it remains zero until Vi reaches the Vb when Q1 turns on and it starts conducting. So something. So this how the output voltage will like this. This is outer one is our Vi, but the inner one is our V naught, the output voltage. And output voltage will be always less than Vi by this voltage VBE. And there will be certain right time interval, right? Certain period of time where the output voltage will be zero. Right? Output voltage will be zero. And this part is known as the called the crossover distortion. So it's a distortion in the output wave, right? And this distortion we get when the output, right, changes from right positive to negative or negative to positive. And that's why I call the crossover distortion when it's trying to cross right from the positive to negative side. So we have this distortion in the output signal. Is that clear, guys? Any question?
Yes, sir. Clear, sir.
Yes. So with this circuit, we can get both the positive and the negative half cycle, but only problem remains here that we have a distorted output, right? It's not completely sinusoid, but there is some distortion. Now, how we can overcome this distortion? This distortion we are having because Vi has to supply the for this base to emitter forward bias voltage, right? So if we can provide this the bias voltages in some other means, right? Maybe we can uh, overcome this, or we can remove this distortion. Right? The basic concept, right, to provide the forward bias voltage to these two base to emitter junctions, we can show like this: that you put two diodes in series. You put two diodes in series, and you provide some forward bias current here, ID, right? So that VD, right, the forward bias dart voltage here, right? Since these are PN junctions, right, and this is also PN junction, so two forward bias, this voltage will provide enough, right, voltage to this PN junctions to make them forward biased, so that when you apply the signal here, You can apply the signal here, Vi. So now Vi does not have to provide these forward bias voltages because these forward bias voltages are being supplied by the diodes, right? The two diodes. Right? Is that clear, guys? This is shown as VB. Now, the voltage here will depend on this bias current, and this is very critical here because you don't supply too much voltage here, right? So, if this is too much forward biased, then this will, carry high current, right? High current will start flowing, right? And that will, you know, draw large power from the battery and it will have heat dissipation. You don't want that, right? So you want them to be just forward biased, right? With minimum current flowing here. So if you look at the diode characteristics, the diode characteristic is something like this, right? You have, let's say, voltage VD and the current here, the diode current ID, right? So with the increase in the voltage, diode current initially remains almost very close to zero. After a certain voltage, start shooting up, right? Start increasing exponentially. So this voltage, what the current starts picking up, this voltage is called, do you know what this voltage is called? Do you remember? That is called the cut-in voltage, right? It's called the cut-in voltage. Hello guys, are you there?
Yes, sir.
Yes, sir.
Do you remember this term, cut-in? This is the voltage where the current just starts picking up, right? Starts rising. And below this voltage, current remains almost very close to zero, right? Negligibly small. So this, the VD, right, should be equal to this cut-in voltage, right? So that, they are just forward biased, but not carrying any current or negligibly small current. So that is how this, they should be biased. And that will depend on how much current, right, you are pushing through these diodes, right? And so and using the diode equation, and what is the diode equation? Diode equation will be expressed like this. ID is IS, right, the reverse saturation current, and then e to the power, the VT by VT minus 1, right? And here VD should be your cut-in voltage, right? And cut-in voltage usually it will also vary from diode to diode, but usually between 0.5 to 0.6 volt, right? So depending on the diode, what is the cut-in voltage? So if cut-in voltage is 0.5, so you can determine IS is a constant. So you can determine ID, what is the ID, what should be the ID. And then you design the current source accordingly and push that current through these diodes, right? So that the voltage that will be generated by these two diodes will be just enough to forward bias this current, these two base emitter junctions without causing, any significant current flowing through these transistors. Is that clear, guys? Any question?
No, sir.
Okay. I'm just trying to give you the basic concept without going into the more detailed, theoretical aspects of this. And so this is the conceptual, actually, the circuit, how we can provide the bias current and overcome this, the distortion, this crossover distortion here. You see that voltage here is fixed once this, you fix the current, this bias current. So now here when the voltage rise and fall, right? This is how it will change here. we are applying voltage at, you may feel that voltage we are applying to this, this particular, this transistor. What about this one, right? So when voltage goes negative, it understood the voltage are going negative, this will turn on and will go. How about this one? See that when voltage is going up, right, for positive voltage, when this voltage is going up, since this voltage is all fixed, so this voltage here also goes up, right? Because this voltage is, if you have whatever voltage here, you have, let's say here you have VI, so here voltage will be VI plus 2 VD, right? So with the rise in the voltage at this end, voltage here will also rise, right? And then this will push this transistor further deeper into the forward bias region, and heavy current will start flowing through this, right? And voltage when goes negative, this will, push this, transfer further deeper into the forward bias region, and this will turn on heavily and pull large current, right, through the load and through the transistor. And this is how the circuit will work. And but again, this is not the actual circuit that is used in the, this is actual, real, the output stage, this amplifier. The real side actually, these diodes, instead of diodes, transistors are used again to provide this forward bias voltage. So this is circuit that is actually used to provide the forward bias voltage for these two PN junctions. Now, how does it work? Now we are pushing this current right through this. It shouldn't be ID, right? It should just I, let's say. Now part of this current will go through this. Now, this is a forward bus, let's say the base emitter voltage forward bus. So that will determine how much current will flow through R1, so R2. So IR1 here we can write as VBE1 divided by our IR1. So VBE1 by R1. Sorry, R2, right? R2. So this voltage divided by this resistance, this voltage across this resistance is VB1, this base emitter voltage. So divided by this resistance will be the current IR1. Now the same current we assume that's flowing through R1 because this current will be much smaller, assuming it's very much small. Base current is small, base current flow, but negligibly small compared to this current. So if we ignore that part, so then this voltage from here to here, which is the VBB, the total voltage, right, will be, we can write as I R1 times R1 plus R2. Right? So current times the total series resistance. And IR1 is this, which is VBE1 divided by R1, and that times R1 plus R2. Right? And that we can express, if we take R1 inside, express as VBE1 times 1 plus R2 by R1. Is it R1 or this R2? Sorry, I made a mistake. Okay, so that was a mistake. So then it will be R1 by R2 plus 1. So basically what this circuit is doing, right? Basically this circuit is producing a voltage, right? That is proportional to this base emitter voltage VBE. So this is actually multiplying this voltage VBE by a factor, which is 1 plus R1 by R2, right? So this circuit is also therefore known as the VBE multiplier. Basically, this is multiplying, producing a voltage, right, that is proportional to this VBE, and this multiplying this factor is 1 plus R1 by R2. And we can easily adjust, right, this voltage by varying either R1 or R2, right, and have the appropriate voltage that is needed, right, to just forward pass these two phase emitter junctions, right, without drawing much current. Is that clear, guys? Any question?
No, sir.
Yeah. Okay. And if you are applying this voltage here, so instead of directly applying this voltage here, this is usually applied through a voltage buffer. So can you identify this configuration here? Hello guys, what is the configuration? Hmm? What is the configuration of this one? Hello, have you all gone to sleep? What is the configuration of this one? Should be able to answer this very basic question. So I leave it up to you to figure it out.